Alright, so this is active filter design lecture 6. In the last class, we were discussing the inverse Chebyshev approximation, where the idea is somewhat analogous to the Chebyshev approximation. In the Chebyshev approximation, we saw that we wanted ripple in the pass band. We didn't really care what happened in the stop band. All we said was we'll take whatever we get. Here the specification is the dual. So in the inverse Chebyshev, you want the transmission of the filter not to exceed a certain maximum. The DC gain is 1. This refers to the stop band edge frequency, and we don't really care, or we don't attempt to do anything about the pass band as long as the DC gain is 1. And we said that yesterday we saw that if we did look at this a little carefully, we see that there are very many similarities between this and the Chebyshev response that we saw before. And there's ripple in the stop band here, whereas there's ripple in the pass band, which therefore led us to believe that we don't have to go and do an approximation all over again. What we could do is use all the knowledge we had built up during the Chebyshev approximation and manipulate the stuff a little bit, and we should be able to get this. And sure enough, we did that. One thing that we did notice, however, was that this cannot be an all pole filter because there are zeros of transmission on the j omega axis. So, and sure enough, when we finished the whole process, we ended up with mod h of j omega square is epsilon square Cn square of 1 by omega divided by 1 plus epsilon square Cn square of 1 by, right, where Cn is the common Chebyshev polynomial that we know. Let's take a simple example. N is 3. Okay. So the denominator polynomial of the Chebyshev filter is given by, when S is j omega, is given by 1 plus epsilon square C3 square of S by j, right? Okay. And we equated this to 0 to get the poles. That will give us the poles of the Chebyshev filter. The poles of the inverse Chebyshev are simply, to get the denominator d of s for the inverse Chebyshev, what do you need to do? Replace s by 1 by s, or equivalently, if the original polynomial was a1 s cube plus a2 s square plus a3 s plus a4, then the polynomial for the inverse Chebyshev will be a4 plus a3s plus a2s square plus a1, right? So a1 s power 4, right? So all that we need to do is find the polynomial for the Chebyshev, right? And then do this simple flip. And how do we find the polynomial for the Chebyshev denominator? We know the roots. From that we find the, once you know the roots, you know the poles in the left half plane from which you can find the polynomial. So the poles of the Chebyshev are given by S must be, what did we say yesterday? Sine of 2m plus 1 into pi by 2n, which is 6, right? Sine hyperbolic inverse 1/3 of sine hyperbolic, sine hyperbolic of 1/3 sine hyperbolic inverse of 1 by epsilon, right? Plus minus j cos of 2m plus 1 pi by 6 cos hyperbolic of 1/3 cos hyperbolic inverse of 1 by epsilon. Sorry, that's, thank you, sine hyperbolic inverse of 1 by epsilon. Okay. Now we have to run this through for various values of n, correct? So the values will be plus minus sine, for m is 0, plus minus sine pi by 6 sine hyperbolic 1/3 sine hyperbolic inverse 1 by epsilon, okay, plus minus j cos pi by 6 cos hyperbolic 1/3 sine hyperbolic inverse 1 by epsilon. And then the only thing that keeps changing is this becomes sine 3 pi by 6, okay, then this becomes cos 3 pi by 6, pardon? Yeah, but then you go across the entire circle, right? So you will end up with, if you end up with a plus jb, you will end up with minus a plus jb, minus a minus jb, and a minus jb. So all the four. If you end up with this, I've already covered. If you get this, then you must end up with this, and this. This is because of real coefficients. This mirror image is because of d of s and d of minus s, right? So which of these, and then you will also get sine 5 pi by 6 blah blah blah, okay, whatever, plus minus, okay. Obviously there will be many redundant roots, they all coincide. So the stuff that you want, the poles that you want are P1, which is P1 slash P2, which are plus minus minus sine pi by 6. You want a negative real part, sine hyperbolic 1/3 sine hyperbolic inverse of 1 by epsilon, plus minus cos pi by 6 cos hyperbolic of 1/3 sine hyperbolic inverse of 1 by epsilon. This is a pole pair that you want. How many poles are you looking for? 3 poles. Another pole P3 is given by minus sine 3 pi by 6, which is pi by 2. So minus sine pi by 2 times sine hyperbolic of 1/3 sine hyperbolic inverse of 1 by epsilon. Pardon? Oh, sorry. Yes. Okay. So the Chebyshev denominator will be 1 plus s by P1 into 1 plus s by P2 into 1 plus s by P3. Okay. You could also do it as, s minus, 1 minus, okay. P1 is a pole, right? So must be this, okay. So, or you can do S minus P1 and S minus P2 and S minus P3, they're all one the same thing. Once you find the Chebyshev denominator, all that you need to do is to find the inverse Chebyshev denominator is to interchange the order of the coefficients, okay. All right. So let's call this 1 plus A1s plus A2s square plus A3 s cube, where A1, A2 and A3 can be found out by simply multiplying out all these factors. Is that clear? And therefore, the inverse Chebyshev denominator will be s cube plus A1s square plus A2s plus A3. You can divide throughout by A3 to get 1 plus A2 by A3 times s plus A1 by A3 times s square plus 1 by A3 times s cube. The idea is that the denominator evaluated at DC reduces to 1. If you put the numerator also in the same form, then the DC gain will be 1. Is that clear? We still have to find the numerator. So the numerator is 1 by epsilon square Cn square of 1 by omega, which is you want to find the zeros of the numerator. So this is the inverse Chebyshev denominator. The numerator goes to 0 at to find the roots of the numerator, all that you do is equate Cn of 1 by omega to 0. And what is Cn of, and what are the omegas? Do you think they are going to be greater than 1 or less than 1? At what frequencies will the zeros of the inverse Chebyshev occur after the stop band edge? So omegas at which you would expect zeros are all greater than 1, which means that 1 by omega is less than 1. So which form of the Chebyshev polynomial will you use? Cos of 3 cos inverse 1 by omega 0. Okay. So pardon? Yeah, sorry. Yeah. The numerator is epsilon square Cn square. Thank you. 0, which means that cos of 3 cos inverse 1 by omega is 0, which means that the argument must be of the form 2m plus 1 into pi by 2, which means that cos inverse 1 by omega must be of the form 2m plus 1 into pi by 6, which means 1 by omega is cos of pi by 6 cos 3 pi by 6 cos 5 pi by 6, etc. Okay. You know that if plus omega is, if it goes to 0 at plus omega, it also goes to 0 at minus omega. Okay. All right. And so the notch frequency, the frequencies at which the notch happens are 1 by cos pi by 6, right? Okay. What is and 1 by cos pi by 2, which is what? Infinity. So there is, so it basically means that there are, for the third order inverse Chebyshev, there are 2 finite zeros and 1 zero at infinity. So the numerator should be written as 1 plus s by j omega x, 1 plus s by minus j omega x times 1 plus s by infinity, correct, which therefore will simply reduce to 1 plus s square by omega x square omega x1 square, okay, where omega x1 square is 1 by cos pi by 6. What is 1 by cos pi by 6? So 2 by root 3, I mean omega x1 square will be 4 by 3. Okay, it's greater than 1 as we expected. Okay, so we found the numerator and the denominator. So h of s is therefore 1 plus s square by omega x1 square divided by this d of s, which we have found earlier. And how will the response look like? It will be 1 at DC, it will be epsilon by square root of 1 plus epsilon square at the stop band edge, which is 1. Okay, we still don't know how this goes between here and there. All that we know is it's monotonic, right, because the Chebyshev polynomial ripples and keeps going up ad infinitum. Okay, so when you do all this flipping, flipping and flopping and all that stuff, it still remains like that, which means that this must monotonically fall from unity. Okay, and then it does this. There must be only one in the positive omega axis. There must be only one 0, right? So that must be at omega x1, and then the second 0 is at infinity. Now, if you have an even order inverse Chebyshev, what do you think will happen? If you have an even order Chebyshev, how will it look? You have to find the numerator will have to be, for example, 1 by 4 cos of 1/4 cos inverse of 1 by cos of n cos inverse 1 by omega must be 0, which means that 1 by omega, the frequency at which there are zeros of transmission, must be 2m plus 1 into pi by 2 into 4, which is 8. So this will go to 0 at pi by 8, 3 pi by 8, 5 pi by 8, 1 by omega must be cos of this character, which is cos of 3 pi by 8, etc. Okay, cos 5 pi by 8 is the same as cos 3 pi by 8, is the negative sign. Okay, and therefore you see that pi by 2, cos pi by 2 is not a part of the series. So therefore it means that all the poles are at, all the zeros of this equation are at finite frequencies. So you will get something of the form 1 plus s square by omega x1 square times 1 plus s square by omega x2 square, where omega x1 is 1 by cos pi by 8 and omega x2 is 1 by cos 3 pi by 8. So a fourth order inverse Chebyshev response will look like this. So if I assume that this is 1 and this is epsilon by square root of 1 plus epsilon square, okay, and this is unity, then it will do this, and keep doing that. Oh, Oops, making too many mistakes today. Yes. Okay, and this makes sense because if you have, specifically the transmission at infinity is epsilon by square root of 1 plus epsilon square. That makes sense because the numerator is 4th order, right? The denominator is also 4th order. So if there is an s power 4 term in the numerator and s power 4 term in the denominator, obviously as s tends to infinity, the transmission will simply be the ratio of the coefficients of the s power 4 term in the numerator to that in the denominator.
This cannot be practically realized.
Why can't this be practically realized?
Most components will have a frequency roll-off which was infinity.
No. All I am saying is with ideal inductors and ideal capacitors you can do it. Okay. I mean, nothing in the world is, there's no ideal inductor in the world and there's no ideal capacitor in the world. Okay. Which basically means that all the stuff that we are learning is all bogus. You understand, right? Okay. Everything, it turns out, is a special case of a transmission line, right? An inductor can be thought of as a transmission line with a very high characteristic impedance at a very small length, and a capacitor can be thought of as a transmission line, a special case of a transmission line with a very low characteristic impedance and again a very short length. The moment the physical dimensions of the components start to become an appreciable fraction of the wavelength of at which of interest, you find that these classical approximations or the classical elements 1 by s and 1 by sc and sl are no longer valid, okay, because of distributed effects, and therefore these things don't really hold true. But in practice, you get to in many practical situations, the frequencies you deal with are much smaller than, at those frequencies still you can treat the circuit element as a lumped element. Okay, that's what all the networks that you've learnt are all what are called lumped elements, where stuff is not by lumped it means it's not distributed, all right. And also there is this common belief that RF means only very high frequencies, right? Or okay, it's not necessarily true at all. High frequency is simply, there's nothing absolute in high frequency, right? You can't say, maybe for 100 years back when people were doing AM radio, right? Then 600 kilohertz was considered RF and high frequency. That's because all the components they had to work with were this big, right? Today you do 600 kilohertz experiments in the lab, okay, and maybe 50 years, let's say even 30 years back, people would consider like 4 and 5 megahertz is RF, okay. Again, 4 and 5 megahertz you can do in the lab today because the component sizes have become very small. And 15 years ago, people thought gigahertz was was RF, okay. But today's dimensions of devices have reduced so much that on an IC, whether you're doing designing circuits at 1 gigahertz or 3 gigahertz, it doesn't really matter because the sizes at 3 gigahertz, the wavelength of light is about 15 centimeters or so in a dielectric, okay. Whereas the IC sizes that you're talking about are a fraction of a millimeter. So you can see that there's still the physical extent of the device is much smaller than a wavelength, which means that you can still, for all practical purposes, treat a capacitor as a lumped element. In practice, also another thing you have to bear in mind is that all these things assume that the capacitor is a lossless element, right? The 1 by s means that the voltage and current are 90 degrees out of phase, right? But in practice, you know that there's no lossy element, there's no lossless element, everything is lossy, okay. To that extent, you have to figure out ways in which you kind of minimize the loss or use better materials and so on. You understand? Okay. So, yes.
So, like the region it goes to, it doesn't go to at omega equal to infinity. If the region given was numerator is also fourth order derivative. So for third order.
For third order, what happens is one of the poles is at infinity, one of the zeros is at infinity. So the polynomial becomes 1 plus s by infinity. So it is indeed only a second order polynomial. You understand?
Sir,
Yeah.
can I, is it possible to have a rippling in both the bands and have a
Yeah. So I'll come to that. Okay, the question asked was, is it possible to have? So we've seen three examples so far. One, Butterworth, where there is no ripple at all either in the pass band or in the stop band. The Chebyshev, right, where there is ripple in the pass band and no ripple in the stop band, or what is called a monotonic stop band. Okay. And then in the third example, where there is no ripple in the pass band, but there is ripple in the stop band. And for those of you who have done your assignments, you will find that for the same attenuation spec, okay, a Butterworth, the order of the Butterworth required is much higher than the order of the Chebyshev, okay, and the reason being given is that you are able to tolerate ripple in the pass band, okay. So if you go and do the math, it will turn out that the order of the Chebyshev and the order of the inverse Chebyshev required for the same brick wall spec is the same, okay. So whether you have ripple in the pass band or ripple in the stop band, you will be able to get, you're doing much better than if you insist on having a flat response, okay. So now the obvious question is, if I now allow for ripple both in the pass band and in the stop band, then shouldn't I be doing better than the Chebyshev and the inverse Chebyshev? Do you understand the argument, the intuition? Okay. If things are maximally flat, you know, I'm getting some kind of transition band width. Okay. I'm able to do better if I don't insist on a flat pass band or a flat stop band. Okay. So if it follows that if I don't insist on if I don't mind ripple in both stop band and pass band, I should in principle be able to make the transition band even sharper, and it is indeed true, and those families of filters are called elliptic filters, okay. To go through the math gets extremely complicated, and I therefore don't do it. It probably takes 3 or 4 weeks to just get through the derivation of the elliptic filter stuff, okay. And the math is nowhere as simple as this, okay. This itself, I probably think many of you are driven to the edge, right. The elliptic stuff requires Jacobian elliptic functions, and the stuff is actually quite complicated. So the next best thing is to say ellip open bracket 2 dB ripple in pass band, 40 dB attenuation in stop band, 5th order, close bracket, hit enter, and then MATLAB will give you all the polynomials, right. So of course you could have done all this stuff even for the inverse Chebyshev and the Butterworth, but I thought it's fairly simple stuff, and you should have some idea of where all these things how all these things come about, okay. All right. Now one last remark I need to make about the inverse Chebyshev is, we have seen that in the passband it's monotonic, but we'd like to see how the passband behaves, right. We know that at DC it is 1, right, but around DC how does it behave is something which is of interest, and let's try and quickly mod h of j omega square for the inverse Chebyshev is 1 by 1 plus 1 by epsilon square Cn square of 1 by omega. This is what we derived, okay. Cn square 1 by Cn square. Okay, and we are interested in the behavior of this at low frequencies. So as omega tends to 0, 1 by omega tends to infinity, okay, and Cn, which is cos hyperbolic of n cos hyperbolic inverse of 1 by omega, will tend to, what is cos hyperbolic inverse of 1 by omega as omega becomes very small? This is approximately ln of 2 by omega. All of you are familiar with this? Okay. All right. So cos hyperbolic of n cos hyperbolic inverse 1 by omega tends to n ln of 2 by omega. Correct? Which basically means that cos hyperbolic of ln of, this is nothing but cos hyperbolic ln of 2 by omega whole to the n. Okay. And what is cos hyperbolic? So as the argument, as this becomes larger and larger, this also becomes larger and larger, which means that cos hyperbolic of a large number is approximately equal to 1/2 e to the power of the argument. The argument is log of 2 by omega to the power n, which basically means that this must be 2 by omega to the power n. Is this clear? So therefore mod h of j omega the whole square is 1 by 1 plus 1 by epsilon square times 1 by 4 2 by omega whole to the power 2n. Is this clear? Which is 1 by 1 plus 4 by epsilon square omega by 2 whole to the power 2n. Does it make sense? Okay, can somebody comment on this? I mean, okay, this has the same form as that of an nth order Butterworth filter, okay, except that 3 dB bandwidth is different, but you can't expect the 3 dB bandwidth to be the same, because in the inverse Chebyshev, omega equal to 1 was the stop band edge, okay, all right. So, but all that you can say here is, I mean, if you obviously therefore the normalizing factor is not of concern. But the key point to note is that at omega equal to 0, you have what kind of behavior? Maximally flat behavior, right? The kind of maximally flat behavior you can expect for an all pole filter, which is the same as the Butterworth approximation.
So it is only approximately like because it makes an approximation.
No, the only thing we are doing is I'm trying to evaluate the stuff at omega equal to 0 in a small region around omega equal to 0. I mean, which is what we did for the Butterworth anyway, correct? In the Butterworth, what did we do? We said we're going to equate the value of the filter as well as all its derivatives to 0 at omega equal to 0. In other words, this is the, I mean, that is the behavior. Around omega equal to 0, this behaves like the Butterworth, and we know that this is also monotonic, right? Because the Chebyshev monotonically keeps increasing beyond the stop band, right? Which means that when you flip and flop and all this other stuff, in the pass band, it must monotonically approach 1 at DC, right? And this also indicates that around DC, this is as flat as it can, I mean, is as good as the Butterworth. So clearly, you can see here, therefore, that the pass band is as good as the Butterworth, right? Can you comment on the transition band in the inverse Chebyshev? Do you think it's going to be better or worse than a Butterworth? It's better because you have zeros, okay. This is the Butterworth, okay, and the inverse Chebyshev is probably something like this, but then it's got zeros, okay, something like this, okay. So the zeros of transmission help in making the transition band much sharper than the Butterworth.
So also, sir, sometimes if you want to kill a particular noise signal which is
Yeah. So another observation is that if you deliberately want to remove one particular component, then you can always place you can tune the stop band edge such that the zeros fall on that frequency. But if the zero moves off slightly, then the cancellation is never perfect. Okay.
In the region slightly after omega equal to 0.
Just conclude this part. So therefore, we have seen Butterworth, Chebyshev, inverse Chebyshev. We figured out how to find h of s. The next step is to realize h of s using passive elements. L, C and R. Okay, and there is a motivation for the kinds of networks that we'll be using. Okay, again, as I said, a lot of this dates back to telephony, right, where the source is modeled as a voltage source with some internal resistance Z0, okay, and the load turned out to also be having an input impedance of Z0. So when people made these amplifiers, they would make the output impedance Z0 and the input impedance to be Z0, and no, Z0. Z0 is real. Okay, all right, and to make a filter, therefore, you would need to put a network inside between the source and the load, okay, to realize the required filtering function. Okay, and it made sense to use only lossless elements inside this box, because while there are deeper reasons for this. One thing is that the moment you deliberately introduce resistors inside the box, then presumably you are losing some useful power that could be delivered to the load in the resistors inside the box. Okay, so people said, hey, it seems like a smart thing to do, to just use L's and C's inside the box. Okay, anyway you have the R's, the Z0 at the input port and the output port are resistors. Okay, and in principle I need inductors and capacitors and resistors. The resistors are already there. So let me see if I can have only inductors and capacitors inside the box. You understand? And if you have 3 inductors and 3 capacitors in a box, they can be connected in any number of ways. Okay, so first thing we will consider are we have only done low pass filter approximations. So we'd like to synthesize low pass filters, and the first thing we did was all pole low pass filters. So we will try to synthesize all pole LC filters. Okay, and this LC network is some kind of special network in the sense that it is terminated at both ends. Okay, right, with resistors Z0. Okay, so this is what are these such families of filters are what are called doubly terminated. LC filters. Okay, and what do you think is a reasonable choice for the topology of the LC network inside? If you want to have only poles, you don't want to have finite zeros, what do you think you should do? Okay, well, what I would do is start with the basics, right? So the first order filter would be this, right? This is Z naught, this is Z naught. If I want to make it second order, what will I do? Pardon? When I want a low pass filter, if I want if I want to use an inductor, then this is a low pass filter. Why didn't I put an inductor in series with the capacitor? That will also give me low pass operation, isn't it? It will have finite zeros. Putting an inductor in series with the capacitor at high frequencies, what will happen? The inductor becomes an open, correct? So therefore, at high frequency, the gain will be 1/2. If I put an inductor in series with this capacitor at high frequency, this will be not there, and the gain will be 1/2. But that's not what we want. We are trying to synthesize all pole low pass filters. In other words, at infinite frequency, the gain must be 0, right? Whereas if you did this, right, at infinite frequency, what's happening? This is becoming an open, this is becoming a short, okay? So it's like simultaneously opening this as well as shorting this, okay? So that's why you get the second order roll off at infinite frequency. So now, can you extend this to higher order? Yeah, so there are many, so the basic idea is to do something like this, blah blah blah, okay, or you could also, for example, put the inductor first, capacitor next. This is a capacitor, inductor, capacitor, inductor. You could alternately put inductor, capacitor, inductor, capacitor corresponding to either a T realization or a pi realization for the basic section. Okay, so what does this resemble? It's a ladder. This reminds you of the rungs of a ladder. So these are called LC ladder filters. And since they are doubly terminated, okay. Another advantage, another minor point is that these are what are called canonical structures. In other words, if you have an nth order transfer function, what is the minimum number of reactances you need to realize the transfer function? It's n. Okay, so that's the minimum you need, and an nth order ladder filter will have a sum total of n inductors plus capacitors. Okay, so the number of elements needed here are the minimum. Though this may not be the only way of realizing an nth order transfer function, this is definitely not a bad way to start. You understand? Please note that it is also possible to get order n by using more than n inductors and capacitors. A simple case in point is replace every inductor by 2 inductors in parallel, every capacitance by 2 capacitors in parallel. Now I have 2n inductors plus capacitors, but the order is still n because I wasted all my elements making capacitor loops and inductor cut sets. Okay, so in that sense, an LC ladder is canonical. It does things as efficiently as one can imagine, right? And the only sources of loss in the whole network are the source impedance and the load impedance, which we cannot avoid. Okay, so these are called doubly terminated LC ladder filters. Now, given the transfer function, we'll have to figure out how to synthesize the values of, how do we get the values of the inductors and the capacitors. Okay, so we'll meet tomorrow, and then tomorrow 9 o'clock, same room.